Welcome to Hartman Math. Before we get to our lesson on polynomial functions of higher degree, let's do a little warm-up review of lesson 2.1. Go ahead and pause here, work through the problems, and resume when you're ready. All right, number one, you should have gotten f of x or y equals negative 1/2 quantity x plus 2 squared plus 5 as our quadratic function in standard form. For number two, you should have gotten 28,800 square meters. Probably want to label this as x, x, and y. And then the perimeter becomes 2x plus the 1y would equal the 480 as your constraint. And then standard form, by completing the square, f of x equals negative x minus 5 squared plus 21. This is lesson 2.2, polynomial functions of higher degree. Here, if we look through, it's going to talk about continuous functions. Polynomial functions are continuous, meaning they have no breaks, holes, or gaps. So polynomial, not polynomial as it has a break. Polynomial, nice and smooth. Not polynomial, straight edges. So polynomial, polynomial, continuous, smooth, and so on. So we're going to kind of start off with some polynomials, functions of higher degree that have similarities to smaller degree functions that we've already looked at, maybe back in 1.6, our library of parent functions. So if we look at this one, the characteristics of raising to the 6th power, as that is an even power, is very similar to raising to the 2nd power. If you remember our x squared, our squaring function. In fact, if we focus on the 3 key points, it's going to have the same key points. So we kind of remember our transformations where we would have a parabola and we would shift it right 3 and then reflect it about the x-axis. And then we've got our parabola. The difference between this one to the 6th power and x squared is that it's going to go down faster. It's going to be a narrower parabola in shape because of the higher exponent. Whereas if this was x squared, we would have had a point right there. That's another fairly important point. But this, as you can see, this one's far inside of that, as if it were going up, it would grow very fast. All right, for part B, g of x, x to the 5th plus 2, I think that's going to be very similar to x to the 3rd plus 2. If we remember our x cubed, cubing parent function, which had key points here, here, and here. So we're just going to translate or shift this up 2. So the center point goes to there. And kind of the same idea. The higher this exponent goes, the faster that it's going to shoot up and grow. But it's going to continue to go left and right forever. As we know, for the polynomial functions, the domains are going to be all real numbers from negative infinity to positive infinity. So dealing with a polynomial function, we're going to look at the leading coefficient test. What happens out at the edges of the graph. So when our degree, n, is odd, it will start low and end high when the leading coefficient is positive, so no reflection. Starts low, ends high. You could say as x approaches negative infinity, f of x approaches negative infinity. As x approaches positive infinity, f of x approaches positive infinity. This book likes to say it falls to the left and rises to the right, which is fine. I typically say starts low, ends high. But if you're doing something in WebAssign, you probably want to stick with that. Falls to the left, rises to the right. Same thing if our n is odd, so let's say it's x to the 9th, something like that. If the leading coefficient is negative, so let's say it says negative 2x to the 9th, it's going to reflect, and it's going to start high and end low, or rises to the left and falls to the right. We're not sure at this point what's happening in the middle, so that's why they're kind of showing this dotted. We don't know, but we do know the end behavior, what's happening at the edges as x approaches negative infinity, as x approaches positive infinity. Now, when our degree is even, like x squared, it's going to start high and end high as long as our leading coefficient is positive. So it's going to rise to the left and rise to the right. If the leading coefficient is negative, it's going to flip, start low, end low, falls to the left, falls to the right. We're talking about an even degree. So we're going to describe the left and right hand behavior, the end behavior of the graph. And we start with the degree. The degree is 8. So it's even. And then we're going to look at our leading coefficient, which is negative 3. The most important thing there is that it's negative. So that's going to reflect. So we're going to start low and end low. It's going to fall to the left and fall to the right. What about g of x? What's the degree? Highest exponent. The leading coefficient is positive. So much like our x cubed parent function, x to the 5th also odd. It's going to start low. It's going to end high. So falls to the left, rises to the right. Now let's see if we can determine what's happening in the middle of the graph, which could be helped by the real zeros of the polynomial function. The function has at most n real zeros if we're talking about a polynomial function of degree n. We'll get more into that later in this chapter. This is a question that they like to ask. What is the maximum number of turning points? Not necessarily how many turning points it has, but at most it would have n minus 1, one less than the degree, that many turning points. Okay. Turning points are also called relative minima or relative maxima. It happens where the graph changes from increasing to decreasing or vice versa. All right, this part is really important. These four things are interchangeable and essentially synonymous. If you know one of those, then you know the others. Such as, if we know x equals a is a zero of the function. So say, all right, I got this function f of x. I know that 10 is a zero, meaning that if I plug in a 10 for all the x's, the answer comes out to be 0. Well, that means that if we turn it into an equation, instead of f of x equals 0 equals, then 10 is then x equals 10 is a solution of that equation. Probably more importantly, it tells us that x minus 10 is a factor of the polynomial function. And if we were to graph it, 10 comma 0 would be an x-intercept. So if we know one of those, we know all of those. Example number 3, find all the zeros of the function, determine maximum number of turning points of the graph of the function. So, to find the zeros, factoring is probably a pretty good strategy for us. I'm not crazy about the fractions. So maybe we could, in terms of factoring, we could factor out the GCF, and that would include the 1 over 2 part. That's going to kind of get rid of our fractions. All right, from there, I think the rest of the factoring should be pretty easy. That factors into binomials. And so we're ready for the zeros. The zeros coming from here, set it equal to 0 and solve. Here and here, we've got zeros of 0, 1, and 3. What is the degree of our function? 4. So what is the maximum number of turning points? Since it's degree 4, one less than that makes 3. Doesn't mean that that's how many turning points it has. Is it for a 4th degree function? What is the maximum number? That's the maximum number. All right, repeated zeros, and we'll kind of discuss this later. 4th degree functions should have 4 zeros in the complex system. We've only listed 3, but 0 is a repeated 0. Because if we factor that out, it's really x times x. If we split it, we get x equals 0, x equals 0. We don't write it twice, but it occurred twice. And if we were to graph this, it means something for the graph as well. What it means for the graph is that essentially instead of passing through the x-intercept there, it would bounce off the x-intercept there. So talking about that graph, here we go. We've got the end behavior. So remember, it's 4th degree, positive leading coefficient. It's going to start high and end high. So we kind of start there. We also have the zeros, 0, 1, and 3. We can plot those. Remember, zeros translate to x-intercepts. And remember, we said it starts high and ends high. And at 0, since the exponent is even, it's going to bounce there. And then since the exponent here is odd and odd to the first power to the first power, we're going to cross and cross at the 1 and at the 3. So all the information is confirmed. Starts high, ends high. Bounces here, crosses, crosses. We got it. Make sure that all the information matches, because if we had kind of forgotten about that and said, okay, it starts high, and I'm going to cross, and I'm going to cross, and I'm going to cross, I'm like, oh yeah, it's 4th degree, I'm supposed to end high, well, let's just do that. I would come around and say, well, what just happened right there? Can't go through an x-intercept that does not exist from our previous findings. So make sure all the information matches. Example number 4, sketch the graph. Let's start by factoring. I think we may want to factor out the negative as well. I see that we also have x to the 3rd in common. If we apply the leading coefficient test, 4th degree, negative leading coefficient, flipped, starts low and ends low. So if we factor it, we're going to get zeros at 0 and 3. And notice I did change the scale on the graph. And we know what it starts and ends with. That's not really a whole lot of information, so we may need to gain a few additional points by substituting in values. Like 1 and 2, something like that. We've got 0 and we've got 3, so maybe 1 and 2, a few more. So if we try 1, we've got negative 1 times negative 2 is 2. And if we try 2, we got negative 8 times negative 1 is 8. That's a pretty good idea. And let's see, if we went with 4, That's going to be way off the graph. And our only other chance is -1. If we plug in -1, we're looking at 1 times -4, so -4. Somewhere around there. So then in terms of the graph, something like that. All right, example number 5. Maybe fake. Write a polynomial function that has these zeros. So I think we want to go back to that list of 4 things that are synonymous. We can turn zeros into factors. So what we have is our polynomial function, whether we call it f of x, p of x, whatever, is equal to, as factors, x minus that, times x minus that, times x minus that, times x minus that. And now, we want it to be polynomial, so we can't have the parentheses, we're going to have to multiply this out. We could do it in any order, but I think I want to multiply these 2 together and these 2 together. So there's kind of a special factoring pattern there, difference of squares. I know they're going to get some canceling. So I'm going to get x squared minus 1 here, x squared minus 9 there. And now we can just do the rest of it. We get f of x equals x to the 4th minus 10x squared plus 9. Take example 5, part B. Write a polynomial function with these zeros. Same idea. F of x equals x minus that times x minus that times x minus that. Now, these 2 being binomials, you might need to be a little bit careful about how we're writing them. So notice I got some brackets here. X minus that one times x minus that one. Now I think to facilitate the multiplication, we may want to kind of reorder this. Distribute the minus and then regroup. Instead of here, regroup with the first 2 together. So if we do that, we distribute the minus and then regroup. It's going to look like this. The reason that we want to do that is now we're looking at this multiplication has a difference of 2 squares. Instead of having to do this with 3 terms and 3 terms where it would be a little bit challenging, we could say, all right, so it's a difference of 2 squares. I know it's going to be an a squared minus b squared model. This squared, negative times positive, minus this squared. So we're talking about x minus 2 squared minus the square root of 11 squared. So this becomes x squared minus 4x plus 4 minus 11. And if you combine those terms, you get this. Now, I will, for whatever reason, the most common mistake is leaving this out on its own and then multiplying these together and then at the end bringing this minus 11, which does not work. This has to be one polynomial. It becomes this. Now multiply them together and we get our answer. F of x equals x cubed minus 7x squared plus 5x plus 21. And that's it for today. I'll see you next time.